Good morning, everybody.
Professor, I'm still not sure if the provided parser is still working with the greater scripts.
Uh, okay. I think Josh put a note on that on Piazza. Was that any help at all, or was that
Oh, I
not
can
enough?
look at it. I saw that he released the bug fix on like the GitHub, and I tried carrying over that bug fix and it's still deleting my parser, but I haven't seen if he made a comment within like this morning.
It could just be because if it's running make clean at all, then it may delete the .o file. But if you just remove that from the script,
Okay, thank you.
let's try that again. Sorry, my Zoom crashed for some reason. Okay, can everybody see my screen and see and hear me? Okay, so as for the question about the greater script, did anyone get this to work when using the provided .o file? So somebody did get it to work. So what was it? Was it just that you have to make sure it doesn't delete your .c file? I mean, you can also do this touch parser.tab to make sure that so the way make works is all it does is it just checks the timestamp of the generated file. So if the timestamp is more recent than the source file, it won't regenerate the .o file. Adding keep where into the make file. Josh mentioned it. Okay, where did he mention it? In Piazza. Okay, so apparently it's in Piazza. So check there if you haven't. Let me actually see. And there's an announcement. Okay. So this is the update. That's a reminder upcoming that there'll be no office hours on 11/20. Okay. All right. So hopefully that's fixed. Oh, this is the keep option here. Okay. Let me keep this chat window nearby. Okay, so today we're continuing on code generation. Last time we talked about function implementation and global variables, and today we're going to talk about how variables and assignment work, and also look at how expressions have code generated. Today is also the due date for the type checking project, project 2, and we'll be beginning project 3, which is covering the code generation stuff that we talked about this week and last week. So just briefly, so Josh and I were implementing this project 3, and I was realizing last night that this is a large project to implement. So we were up to about 600 lines of code, and it would only get larger. So that means the code gen compilation unit would probably be like 1,000 lines of code. And just to explain it all and get it all right is quite intense. So what I decided to do is do some pretty drastic simplifications. So now it's going to be simple C to implement. So instead, in class, we'll go over some of the details of how this implementation would work. But then for what you guys have to implement, it's a much more restricted version of the language. And I'll leave it as a bonus. So I'll give some hints in the project description and some places where you could implement for bonus points or for an extra challenge. So if you want to undertake some of these challenges, let me know, and we can work out some extra credit. But otherwise, it's going to be a much simpler language so that you can get a little flavor of compiling to actual Intel assembly, but without having to do the entire simple C language. So I was a little ambitious in building this in language. So hopefully it'll be a little bit more straightforward to do this. And so all the other stuff in the language will be extra credit. So for this project, you're going to implement function call definitions, function calls, variables, arithmetic expressions, but pointers and control flow we're going to leave for next time. I didn't want to remove pointers from the language. I want to have some amount of pointers so you can see behind the scenes of how they work in C and other languages like C++ that have manual memory management. But a lot of the complexity of the language, like especially some of the more kind of boring stuff, like if you understand how one argument gets passed to a function, then supporting an arbitrary number of arguments is just kind of a generalization of that. And with the Intel ABI, where some of the arguments, the first 6 are in registers and then the rest are in the stack, it's complicated to implement, complicated to explain. There's a lot of things that can go wrong. So here's the simplified subset of the language. So all functions are always going to take one integer argument and always return an int. So that way you won't have to support passing in arrays or returning arrays, which is a little bit tricky with the Intel ABI. And you won't have to worry about variable number of arguments. You won't have to worry about multiple types. So if you have multiple types, each of those has a different bit width, which I'll talk about a little bit today. So characters, for instance, are 8-bit, are basically a single byte. But the architecture supports a minimum of 16-bit words. So there's some tricks you have to do in order to deal with that. So to make this simpler, you only have to worry about integers and pointers to integers, and they're all 64-bit numbers. In C, at least on a 64-bit machine, my machine at least, integers in C are 32-bit versus the pointers, which are 64-bit. And so that means, and I'll show a little bit more today, but that means your type checker and your code generation work together closely to make sure that each type that you're working with, each data type, is using the appropriate register size and the appropriate operation to make sure it's the correct bit width. Getting that right is also a pain. So I've simplified it to just so we can assume that there's only one bit width. So somebody is mentioning that there's a huge spectrum outage. Participation is not that much lower than usual, actually. Maybe it's like, 10 or 15 people lower. But that's unfortunate. I fortunately don't have any outage. And then also there's you don't have to worry about local variables within compound statements. And I'll talk about this more today. I'll give some hints about how you can implement this and what you would have to do to implement it. But already for that simplified language, the kind of detailed instructions, the rules for doing code generation are not that small. It's still pretty, it might be pretty intense to implement this if you're not comfortable with this. So instead of like 1,000 lines for the code generation, it might be 500 or 600 lines with, including the template that I give you for the code. Okay, so there's only 2 source files to download, and the directions are here. But okay, so that's project 3. Functions, implementing functions from last time, and implementing variables, their assignment, their usage, and expressions this time for the next. And so you have 2 weeks to do this, just like with project 3 or project 2. You have 2 weeks. And then project 4, that we'll leave that for the next 2 weeks. We'll go over how pointers and arrays work, and also control flow instructions. Yeah, for code gen, you're generating Intel x86-64 assembly. And I'll show that more, and I'll show that today. So last time we talked about how functions work, how function calls work, if you remember, where the actual architecture, the machine model, is this random access model where there's no kind of intrinsic support for functions, at least in the way we think of functions, the conception of functions that we have when we do programming languages, where not only does it jump to another piece of your program and start executing code, but it also saves the state of that function and restores it on return. And if you remember from last time, making that possible required doing a little bit more than just branching to another function's code. We also needed to set up this complicated information on the stack and make sure that the compiler is aware of exactly where to find all of the data about the function. Its return address, its callers, stack frame, its local variables, its parameters. And so we had this Intel ABI, this convention for how we pass arguments and return values to and from functions in assembly. And it's our compiler's job to make sure that we not only implement functions the way we expect in the language where state is saved, but to also implement this calling convention so that it can interoperate with all the other programming languages and tools on our system. So we're going to go over, we'll review this today, and then we'll go over in more detail how to do project 3. And I'll give examples of the assembly. We'll walk through it. I'll show you how you can debug the output of your assembler. So let's see. Okay, so also project 2 is due today. And before we get started with this week's lecture, are there any kind of pressing questions on project 2? Could not download CodeGen C. CodeGen.c is not found. Okay. Sorry about that. Checkarray. Okay, let's look at Checkarray. Let me first make sure. Let me make sure this is posted. And I, of course, forgot to put it there. Make sure that's published. Okay, it should be there in a minute or two. All right, let's. I don't have a link yet for today's lecture. It's mostly going to be covering Project 3, but I'll put up some. I'll put up some extra notes from today, but there's not much besides the notes from last time and all of the details in Project 3 for today's lecture. Okay, so somebody's asking about Checkarray. Any particular questions about Checkarray? So what's the issue with Checkarray? So let's look at what the type specification says. Okay, so array, I assume you mean array expression, right? Where you're dereferencing an array. So let's see. Okay, let's look at some more concrete example here. So a simple example is this, where A was declared to be, let's say A is declared to be an array of size, an array of integers of size 5. If I'm getting the the second element of this array, then the way we type check this is first we need to make sure that this expression here, this expression A, we need to make sure that that itself is an array first. Now in C, you can also, an array is really just a pointer in C, more or less. So C also allows you to dereference pointers using the same syntax as for arrays. So the same thing in simple C. First we have to do is make sure that the expression that comes before, in this case just an identifier expression. In C you can also do some manipulation of this. You can actually put an expression here. You don't just have to do an identifier. But let's take the simple case of the identifier. So first, check that this is actually of a pointer type or an array type. And make sure that this is, well, let's see, did I say you have to do an integer type? Yeah, so I don't think I provided any constraints on what the type of this can be for this purposes, but really it should be something that can be turned into an integer. With C, that there's some flexibility in doing that, but I just left it as open to do this. So it'll basically be on the problem. If the code gen will have to kind of deal with this, or might cause some incorrect assembly to be produced if we don't check this. But I didn't require you to check that this expression is an int. And then so once we have an array or a pointer as this expression and we do an array access, so say I have an array of 5 integers, what will the resulting type be for this entire expression, this array expression? What will the resulting type be? It'll be an int. Good. It'll be an int. So all you have to do to check this is first check whether this expression A is either a pointer type or an array type. And you know that because you recursively check the type of this expression. So that's the array expressions expression. We're checking the accessing of an, yeah, exactly. You're checking to make sure that the thing you're accessing is an array or a pointer. And then you just unbox that type. So if it's an array of integers, then you just get the type that array is referencing. And same thing with the pointer. If it's a pointer to an integer or a pointer to an integer, then you get the type that the pointer is pointing to. So if it's a pointer to arrays, then you would return that array type. Oh, actually, this index, so I'm looking at my AST. This index has to be a constant integer. I didn't permit, so C allows an expression to be in here, but looking at my AST, I restricted this. Oh no, actually, no, never mind. It's an expression. Never mind, it's an expression. I don't think it's the hardest one. I mean, I think the function stuff is more complicated because you have to loop over the list of parameters and the list of parameter types. But array expression is not much different than like pointer. It's basically pointer dereference. So it's the same idea as pointer dereference. But you just have to make sure. The tricky part is you have to look at the kind of expression node it is and check, is this expression node, is it an array? I'm sorry, you have to look at the type of the expression node and say, is this type an array? Is this type a pointer or something else? In those three cases, for the first two, pointer or array, you just get the type and find the type that it's pointing to. So if it's an array, you check whether it's pointing to a, you get the, let me show you the AST for this. So you just get this expression from array expression, recursively check its type. And then for type, you just check the kind of that expression. And if it's an array type, then the resulting type is this. So you set the resulting type of the array expression to be this type. If it's a pointer, then this is what you set the resulting type of the expression to be. Yeah, so somebody asked, you set the type of the array type to int if it's an array of ints. Exactly, yeah. Let's look at some other questions. Check function is the main problem. Yeah, so in check function, the idea is to, so that's probably the most tricky one because you've got to, let's see, where is it? So I assume you mean the function definition. Is that right? By function, check function? Yeah, so you've got to make sure, you got to check a couple of things. So you have to make sure that so here you've got to make sure that the number of argument names matches the number of argument types. And you've also got to check that each argument matches the type in the same position in that list. So you got to loop over both lists at the same time. So that's the most tricky part. And then you just recursively check the function, add any local variables to scope, recursively check the function body, check the expression, the return expression type, and that return expression, once you have all this, then and then you're done. You want to make sure that this return expression matches the type given in the function signature, given in the return type of the function signature. So somebody says sometimes ident expression prints a type below it and sometimes it doesn't. It's a double check. So I made a mistake and didn't give you the updated AST printer. So make sure you have that. So if it's printing out types at all, for expressions, then it means you have that. It could be that another part of your code is not reaching it. So use the classic debugging technique of getting the smallest source file that triggers that error, and then trace through it either by hand or with GDB or with print statements to make sure that you're actually reaching that piece of code. And you can even put a debugging output, just put a print statement in ident expression and make sure it's actually being reached when you're compiling the code or type checking the code. So it's called call expression. Somebody asked, what is call expression? Call expression is for function calls. That's if you have an expression like say, x equals f of 3. If we have some function defined already, then a function call is this part of the expression. The reason it's an expression is just like a variable, it can be one term inside of your arithmetic expression. And so a call expression is just like a variable access, except you're calling a function instead of getting the value of a variable. So somebody asked, how does Malik work in simple C? So Malik, so as you see with how functions work, all of the local variables get allocated onto the stack. But for variables that you want to live beyond the current function call or the nested series of function calls, then you can also just access basically have random access memory to any of the RAM that's allocated to your program. And so strictly speaking, you can just make a pointer to any place in memory that's not reserved for the kernel, for the operating system, and just use that data at will. So, I could think of it as just a giant array of 64-bit integers, basically, in a 64-bit machine, or whatever bit width you want. But you can think of it like just a giant array. Malik is just a library that helps you manage that space. So it's not something that's built into the language per se, but it's just a library that somebody wrote to manage the allocation of that memory. So there's nothing in the compiler that does any of that help with the heap access for you. Instead, it's just a runtime library where you call Malik and you call free to keep track of what memory you've used already. So really, there's just a table in memory that helps keep track of what memory's been used or not. Malik does a little bit more, so it can also ask the operating system for more RAM space if it needs. It'll communicate how much space the program is using. So in simple C, all we really need to do is link to the Malik library. There's nothing special we have to do in the compiler besides making sure we're able to call functions using the Intel API. All right, so somebody's asking, let's see, for check binary expression, how would you build the cases? So for check binary expression, it's just a giant switch over the operator. So all you need to know, so if you remember, the operator tells you, operator is like a function where it has its own kind of type signature, and you have to check both operands, and the resulting type, as long as those operands match, the resulting type is the return type of those operators. And you really just, for binary expression, you just need a giant switch statement over all the different operators that you have in the op field. So looking at this AST, if we look at binary expression, then you have to check the left and right operands first. And depending on what the op is, so this eop, you check, just do a giant switch and say, well, which operator is it? And then apply the type rules for that particular operator. And that'll tell you what the return type is as well, based on what operator it is. Most of them are same. Most of them either allow any type to be operated on with the same type, and then it returns also that same type. But the logical operators always return an int, because at least in this language, the Boolean value is represented with an int. So somebody asked, why is there only one int in function int? I think you mean this. So this is an illustration of a type error. So if you notice here, this is saying check for incorrect number of parameters. This is an example of a type error. That's why there's only one. Yeah, so somebody's asking when you restore the parent scope. Exactly. So check main is like a mostly implemented function, check function, except it doesn't have parameters coming in. So it should almost be the same. And somebody's asking, should you destroy the scope? So yeah, you should destroy the scope. So there's a global scope, and then each function defines a child scope of the global scope, and then each compound statement defines further child scopes. And so whenever you enter one of the static scopes, create a new symbol table in scope, and then destroy it when you leave that scope. So somebody's asking, they don't get how to get the param types. Param types are part of the functions type. So once you have this function here, there's a field for the declared type. This is what the developer declared the type to be. And within type, it's one of these anonymous union structures. So you have to make sure that it's actually a function type that the developer declared. And then within function type, once you get the, dereference the type and get the function type union member, then you have access to param types. So somebody said they did look at the structs. So hopefully that helps a little bit more looking at these structs. Whoa, lots of questions. Okay. Brackets, yeah. So yeah, in the design of C-like languages, brackets, the open and closed brackets are effectively defining a scope, a static scope. And it's a static scope because the lifetime of the variables is defined basically at compile time, or defined lexically or statically, defined by the grammar itself. Versus dynamic scoping, where the lifetime of the variable is defined by the runtime behavior of the program. So if you call a function, that variable is still in scope in the callee. Somebody's asking why you need to use recursion for checking an array. So I only showed this briefly, but you could have an expression like this to dereference an array, at least in simple C. So you don't just dereference a variable that is of an array type. You can also do some pointer. It's really basically to support pointer arithmetic, which is a very C particular thing. So somebody's asking, do you call the unary expression function? So for all the expressions, instead of having to account for every possible expression that can be used in that nested expression, either in an operand or in an array expression, you just call the check expression function, which dispatches the flow of control to the right expression by looking at the kind of that anonymous union. So nested scopes is just like in C, where I can define a compound statement like an if statement here. And within the curly braces, I can also define X, and it's not a type error because it's not the same X. It's an X that only is, its lifetime is only between these curly braces. In order to support that, well, one way to support that is to make a new scope, just like we make a new scope for functions to distinguish the global versus the local scope. We make yet a third scope for that compound statement. And those nested statements can continue to be nested. Okay, I think I covered all your questions so far, although some of them I'm a little confused on the last one. So I don't know what treating it. I don't know what it is. So 2D arrays, so C does not support, no, there's no treating it like a linked list. There's only the expression here and the expression here within the brackets, the square brackets. So there's no recursion over a list. It's just recursive because the array part, the array expression part, might itself be an expression that you have to recursively check the expression of. So this could also have, like, you know, if you had the right types, you could also have array dereferences within there. Of course, this is not the right types. Yeah, so one use for this possibly is 2D arrays. So somebody mentioned this already, where I can have something like this, where this A1 is dereferenced first, and then I'm dereferencing 2 from some nested array, because C does not have multidimensional arrays per se, but you can kind of simulate multidimensional arrays by having an array of arrays, like so. So I can say an array of 6, or an array of 6 5-element int arrays. Yeah, this is somebody points out that the pointer only points to the first element of the array, and all the arrays in simple C are static. So yeah, that's exactly right. So just like in C, well, an array is really an abstract data type. Well, yeah, I mean, in this sense, an array usually means a contiguous section in memory, not a linked list. But you could certainly define a language where you call the type an array, and then behind the scenes, the compiler is using a linked list to implement that. So it's up to the compiler on how the compiler wants to implement that particular part of your language. But in C, this is exactly right, where the pointer points to the first element. And that's actually why you have base 0 indexing, because this number here is not actually like the ordinal. I always mix these up, but it's not the ordinal number of the element. It's an offset from the first element, because all it does, all this is in C is equivalent. This is equivalent to saying A plus 1 and then dereferencing it. So that's why pointers and arrays are really no different. Just an A2 is just adding 2 to the pointer and then dereferencing it. And you can write, you can play with this in C and see it happen yourself. Yeah, you can think about how sorting on a linked list works versus sorting on an array. But remember, that's the compiler generates code that makes sure that happens at runtime. So you don't have to write a compiler that does the sorting. You just have to make sure that the semantics, or the meaning of assigning. So if I'm swapping 2 elements, you just have to make sure that this assignment works properly. And yeah, in order to implement this assignment, you may have to emit code that loops over the list to find that element and then assigns it. But remember, you're generating code to do that. So once you write that code generation, you're done. You don't have to worry about that anymore as the programmer using the language. That's the beauty of compilers. It's basically like program generation. It's automatically generating code for you. And you don't have to necessarily generate assembly. You could make your own language that generates C, for instance. And this is actually, I think, the original C++ compiler generated C code as its back end before it was, fully fleshed out to generate machine code. All right, so that's type checking. It's due today. There's another office hours after this. So hopefully everybody is making good progress on that. Don't forget that you have a pretty lenient late policy. So if you have trouble with this, or you want to turn it in later and want to move on to project 3, I've also given you a compiled binary that includes both project 1 and project 2. Similar instructions to last time, and hopefully the grading script works out now. Check on Piazza for that. All right, let's move on to code generation. All right, so I talked about how the languages or what you have to implement is now greatly simplified. Let's go over functions from last time. Let's review. Yeah, so submitting one late project is 2% off the project, or 2 points off the project, which is 2% off your whole grade. So 1 point is 1 percentage point in your grade. The graders the TAs are working on the regrading. I think we're probably going to do it every 1 or 2 weeks, just regrade everything automatically. They're gonna set that up, but you can also use the grader scripts to basically regrade yourself. So if you notice that the grading scripts work, or at least most of the test cases, if you notice that works and then you get a 0, then it's pretty easy for you to demonstrate that, hey, my compiler actually worked. And then we just need to check the chain from your computer to the graders running the script. Maybe you forgot to push commit some files, or maybe the grader script is broken somewhere in some particular case. But as long as you can grade it yourself and you find that you're getting the points, it's very likely that you'll get those points, as long as you set up your repository correctly. Okay, so let's review functions. So can anyone tell me the differences between functions in, say, C or a programming language and functions at the assembly level? What are some differences between those? So as I kind of hinted at before, at the architecture level, there isn't really an instruction for, say, do this, call this function. There is a call instruction, but it doesn't really do the same thing that we expect from our programming language version of a function. So somebody said there are jumps. So certainly, yeah, there's branches for both of them. So both of them are the same in that they're changing the flow of control from the callee, from the caller to the callee. I'm going to keep messing those up. From the caller to the callee. So there's a change in flow of control. But you can have if I have a goto in my language, I can write C with goto. How's that different from a function call? So if I've got some main method here, and I've got, I can implement a function by just saying, my function as a label, and I can go to my function. So what makes a function, the semantics of a function in our language, or our invented language like C or simple C, what makes that different from just a mere goto? So maybe I want to have a function that, say, adds 1 to an integer. So if I've got 1, then I'm going to write a function that just adds 1 to x. So naively, maybe I just say, well, okay, x equals x plus 1. So what's wrong with this function here? So functions can make permanent changes. I don't know what you mean by permanent, but okay. So somebody pointed out there's no way to go back when we do this. Yeah, printf never gets run. So we need some way to return. We need some kind of label or at least some way to save what that return address is in our function. Good. So somebody said it creates its own scope. So if I've got, so in this case here, I may also want to call my function on y instead of x. And if I still have I need a different return address here. So what's the issue here? So it needs its own scope. So we solve that by having a parameter. So I can say my parameter name. I can just assume that my param name is my param, or p. And so that way, when I modify P, then that will generalize for any caller of that function. So that's already something that's not done for you at the assembly level. We also need a way to communicate that value back to the caller. And that's what return does. So return communicates that back to the caller. Okay, but we need some conventions to say how those parameters are passed and how they're returned. And just like somebody said, for scope, we also, or at least language designers so far, have used the idea for C, have used this idea of static scope, where within these curly braces, any variables that are declared here, like X in X, for instance, so I could say X equals P plus 1, aren't going to have any effect on X defined between any other curly braces, that it's going to be a fresh memory location. And that's just a language design aspect. You don't have to design your language that way. So you don't have to have nested scoping. You know, I think the original C didn't, I don't think it had, you couldn't declare variables inside of these nested compound statements. You can only declare them as local variables for functions, if I'm remembering correctly. So, okay, so what, so that, I think that covers everything. We need to know the address of the function, because the function just has its own section of code. It's a named set of, it's basically a named chunk of code. We need parameters to be able to pass in arbitrary values that don't depend on where we're calling it. Any position in the code can call that function and pass data, and that function just has its own set of memory that it manages itself. And we need the return value and the return address. We need to know where to return in the function. And if you remember from last time, the way we held all that information was in a stack frame. So the stack frame holds all the information needed to freeze this function when we're leaving and coming back into our function. So somebody's asking, do most compilers store all this information? So this is the kind of tricky part about compilers. So this is the equivalence between the C program or the simple C program and the assembly code. The compiler is not actually executing the code. The compiler just generates the equivalent assembly code. So rather than the compiler having to manage what the actual memory locations are, instead it emits assembly code that at runtime ensures that that memory is managed in the right way. This is what's very tricky to kind of wrap your head around about compilers, is that when we think about the meaning of the input language, the temptation might be to write a program that interprets the meaning of that. So that's an interpreter, or actually executes the code. That's what an interpreter does. A compiler instead has to reason about what all possible programs will do and make sure that the output assembly for all of those programs actually does the equivalent behavior of that input program. So let me show you an example program to see what I mean by this. But by hash tables, maybe you mean the hash tables are used to store and I'll show that more today about how how the compiler actually does this, how it keeps track of these symbols in the compiler, or symbols in the input language. And somebody pointed out, which is why we can get out of bounds errors at runtime on programs that compiled fine. That is, that's exactly right. That's because the definition of the language doesn't require any checking at compile time for those out of bounds errors. And in fact, it turns out that trying to do that at compile time is actually a really tricky problem. It's a very hard problem. And if you use the Turing model of machines, it's actually an impossible problem to solve in general. But there are modern program analysis techniques that can check for out of bounds errors pretty well in a lot of cases. It can approximate it pretty well. And also, you could also have the compiler insert checks at runtime. So when you're compiling your code and you compile an array access, for instance, there's nothing stopping the compiler from inserting a bunch of extra code that says, okay, is this bound, is this index greater than the bound? Then just call an error function, call a function that just runs an error. And that's basically what Java does. So Java has all these checks at runtime to make sure that you're not going out of bounds. C today still avoids doing this, purportedly for performance reasons. So somebody's asking about the hash table thing. So exactly. So the hash table is for storing symbols, the user-defined symbols. So just like in a type checker, you keep a mapping from all of the symbols that the user declared to their types. In the code generator, we keep a mapping from all of the symbols used by the user, by the developer, to basically their places in memory. So we want to know whenever a symbol is used, we want to know exactly where it's going to be found at runtime. The assembly instructions will be, there's documentation for the assembly instructions. So the trick that the compiler uses to know where the memory address will be at runtime is, instead of doing absolute addressing, where it tries to fix ahead of time what the actual address will be, something that won't work if we have recursion. If you can call the function many times, we can't just have a fixed address for each local variable in each function. So the trick is to use relative addressing. So when we have this stack frame, we keep track of the address of the stack frame. That's this base pointer, the BP. So if the compiler can guarantee that BP always contains the address of the stack frame, it does this by making sure it never generates code that overwrites it. And whenever it modifies it, it always makes sure that at runtime, that base pointer will point to the stack frame. We provide that guarantee with the compiler. Then we can always access these local variables as an offset from that base pointer. So it's kind of like accessing an array. Base pointer is like an array where the 0 is pointing to the old base pointer. And when we say base pointer plus one word, or in this case, 164-bit word, so see, this is 8 bytes, plus 1 in that array gets us the first element in that stack frame. Now it's a little bit more tricky, because the stack is actually, each entry is 8 bytes, 64 bits, and the stack grows down from the high address space to the low address space. So what's really happening under the hood is that we're subtracting 8 from the base pointer to get the first element in our stack frame, which is the first parameter, or the first local variable. Subtract -16, that's like accessing the third element in the array, the fourth element in the array. And so you can see here that this notion of arrays in programming languages really comes from the idea of relative addressing at the architecture level. And so there's a special assembly usage that allows you to say, given the address that's in this register, give me the offset from that address. And we can see that here in our assembly code. So here's the base pointer, RBP, and this little syntax says whatever the address in the base pointer is. So its value, so this is where this notion of pointers comes from. At the assembly level, there's no notion of type. So the meaning of the data in a register only depends on how we use it. So if we use this assembly instruction here, this assembly instruction says, go to this register RBP, get its value, subtract 8 from that value, and using that value as a memory address, move whatever the value of RAX is into the address here. So I'm not an expert assembly programmer by any stretch, but there's a few patterns that I'll give you, and we'll go over them today in class. But there's a few patterns for how you move data around between registers and memory. And one of the really common patterns you'll see in compiled code is this move from a register value to an address. And you just have to kind of, look at this multiple times and try writing it to just remember that this is like relative addressing, and that's what's going on here. But the fact that architectures provided instructions like this, where instead of just giving a fixed memory address and saying, okay, move this register value to this memory address, they added these other kind of memory access modes for accessing memory in different ways. So one of the most common ways that a compiler uses is this relative addressing mode, where it's a common idiom to, instead of giving a fixed memory location, you hold a memory location in a register and then move data to that memory location held in the register. So this is exactly what assigning a value to a dereferenced pointer does. This is equivalent to, in C, saying something like dereference X and set it to Y. So if I've got a pointer to an integer here and some integer value, and I do some stuff to assign these, then when I do an assignment to what X points to, this is equivalent in assembly. If X were RBP and Y were RAX, well, let's not use BP. That's sort of bad style. So if X's address, X's value, X also has a register that holds a value. So if RBX, and in pointers, the value is a memory address versus an integer. But the architecture has no idea whether you're using a register for a pointer or not. It's all about how you use the instructions for that value. So this assignment to a dereferenced pointer is equivalent in assembly to doing a move from RAX, which is Y, into the memory location that's pointed to by X. Contrast this with assigning the integer, not a pointer, to whatever Y is, which is moving the value of Y, which is in RAX, moving this to, let me allocate a register here. So let's say it's RDX. So this is saying take the contents of the A register and overwrite the contents of the B register with whatever the A register was. In this relative addressing mode, this says take whatever the value is in the RAX register and move it to the memory address that's found in the B register. So this is saying move to memory address in the B register, whereas this is saying move to the B register. So in the AT&T syntax, the operands are swapped. Just kind of have to get used to that. The Intel assembly reverses this. But you can, so the difference is a pointer is a register that holds an address versus an integer or some other data that you want to work on. And when you work with pointers, it's really just using different memory access modes in the architecture, in the backend architecture. And so I think all architectures have at least some way to have a different instruction for moving between registers versus moving registers to memory or memory to registers. Intel being this CISC architecture where there's lots and lots of different operations you can do versus a RISC architecture. There's no need to specify a different opcode. The assembler will actually figure out which low-level opcode you want to use that you need to use for this addressing mode. And instead you rely on the syntax of the assembler to tell you what you want to do in which addressing mode you want to use. Okay, so let me show one more example here. Say I dereference this X into 2. Can anyone tell me what this might look like? This is a little bit of a tricky question here. So let's say I want to move Y into array element 2, where X, remember, pointers and arrays are the same in C. So what would I fill in here? I know I didn't give you a chance yet to quite digest what's going on here, but let's see if anyone can kind of puzzle this out, what this would look like. So remember that X right now, its value is stored in RBX, and its value is a memory address. Okay, so we've got one answer here, and this is a very good answer. This is very, very close. Not exactly right, but it's very, very close. This is good. This is exactly right. So it's B. Yeah, right. Yeah. I just noticed that too. It's BX. So remember, BX holds the address of X. It's a register that holds a number, and that number we're using as an address. And when we use this relative addressing mode, the move instruction becomes, instead of moving between registers, it's moving to a memory address. And instead of supplying a fixed memory address, we supply a register that holds a memory address instead of holding some value, some integer value. And the person who guessed this guessed exactly right, that we use this to do this in memory relative addressing mode. We put the offset first for some reason, and then put the register that holds the address between parentheses. So somebody pointed out that exactly right, that integers are actually 4 bytes. And I wouldn't expect you to know this, but the Intel, I think, allows this byte addressing, where you can specify instead of words, which are the quad words in 64, I think they're called, where are 64-bit, you can actually address individual bytes in memory. And so I wouldn't expect you to know this, but so that's why this was a really, really good guess. So because this is byte addressing, and because X is pointing to an integer, when we want to move to the next integer in memory, instead of adding 1, we add 4 bytes to move to the next integer, because integers, at least in C on a 64-bit machine, integers are 32 bits, which is 4 bytes. We want to move to the next integer in memory by moving 4 bytes over in memory. And so if we want to get the second offset 2 integers in memory, we go 8 bytes over from the position in memory that X starts at. All right, good. Okay, I'm glad this is making sense. So somebody's asking, how would you subtract from memory address in this? You would just put a negative number. So the assembler will take care of this for you. You just use a negative number to do this. Okay, I know I covered a lot of information there. Some of you at least are getting it, which is great. Questions so far on this? So if you can wrap your head around this, and I'll show the actual documentation of moving in Intel. The manual for Intel is huge. If you can wrap your head around this, then I think you will understand pointers. If pointers have ever confused you in C, which I think they've confused every computer science student, then if you look at how this maps to the actual assembly instructions, it becomes a little clearer why pointers work the way they do, and why they were invented in the first place. Because they're really just kind of thinly wrapping assembly operations, the different modes of moving data in your machine, whether you're moving it between registers or moving it between memory, and being able to do relative memory offsets from relative memory, like when you do array accesses, how you do that at the architecture level. Yeah, so somebody's saying that, yeah, that's exactly right. So that moves you to lower addresses in memory. So if I had, for instance, so if I said -2, which you're actually can you do this in C? C may allow you to do this. I can't remember if C actually checks against this, but if you were able to do this in C, it would correspond to -8. And so, okay, so somebody asked, why would you subtract from memory? So for an array, that's because the definition of the language is that the array index is a positive number. But for our purposes as compiler writers, we want to be able to access negative offsets in memory because of the convention about how the stack is stored in memory. Because we grow the heap from the low address to the high address, and we grow the stack from the high address to the low address just to maximize how much memory both have, just by convention, then we use this relative offsets to negative offsets to start from the space pointer and access the local variables on the stack. So when translating, yeah, I mean, if you're translating arrays, there's really no reason why the user should be, the developer should be accessing negative. That's, I think it either gives you a warning in C, or it, if the compiler is sophisticated enough to find this, or it will just be undefined behavior. So one of the kind of outs that the C language uses a lot is undefined behavior. So instead of requiring the compiler to check things like, well, if you don't assign this variable, it's just going to be some potentially old, stale data from the stack that gets printed out. That's why you get, well, we call it garbage, but that's why you get printed out some arbitrary number if you do this. And the C language doesn't say a compiler has to check against this, but they just say, well, if you do this, I'm sorry, I didn't actually put the X here. So if you do this as the developer, it's basically on you to make sure you don't do this, because this behavior is not something that the C language supports. And so many compilers will just, a lot of compilers will warn you now these days, but the C language does not explicitly say the compiler has to reject this program. It'll accept it, but the compiler is free to generate whatever it wants. It's undefined behavior. So some older compilers will actually have some well-defined behavior for this undefined behavior, causing portability problems between source code. So if somebody was using a compiler that, if they expect this to be 0, for instance, because the C standard doesn't require this X to be 0, then if you're assuming it's 0 and you're writing your code to assume it's 0, if you compile it with a different C compiler, you may get behavior that you don't expect. You're not going to have the same behavior of that program, because this is not, you're not supposed to use this you're not supposed to use this with C. It doesn't have any meaning in the C language. Yeah, undefined behavior does feel a bit like a cop-out, but there are some good reasons for it. I mean, you can be the judge of whether they're good reasons, but so say, if you take, say, buffer overflows. So if I declared this to be a size 5 array and I access 10, this issue especially with strings is, the cause of half of the security vulnerabilities that are due to software bugs, or some crazy, 30%, some crazy amount. I don't remember the actual figure, but some crazy amount of security exploits are effectively due to buffer overflows, which allow you to blow away the stack or blow away other memory in the heap. But there are two tricky issues here. One is that, sure, if I have a fixed number, then that's not so hard to figure out. But if I have a pointer to a string, it's very easy to try to copy this string and forget that there's this null terminator. And so this string is not 5 characters long. This string is 6 characters long, because there's a /0, a null terminator at the end of this. And so if you forget that and you copy 5 characters, you've already, there's no well, I mean, it's easy when there's a fixed array here, but if I'm reading this in from, the user and I forget about that null terminator, then I may easily make a mistake in copying this, or if I don't set the buffers to be the right size. And so protecting against that, the problem is the protection worth it for performance? And so the C decision is that no, the protection is not worth it, because there's all this extra code that the compiler has to insert to check this at runtime. And so from the theoretical point of view, trying to check this at compile time is actually a really hard problem and is subject of like decades of research to see if we can do that, see if compilers can do that automatically at runtime. And so even in more modern languages like Java, if you consider that a modern language, checking that at compile time is even, even Java doesn't check this at compile time. It inserts runtime checks. And if you think about it, you can do basically arbitrary manipulations of strings that make it really hard, that it's really hard for the compiler to track the size of that, especially, particularly if you're reading from user input. The compiler has no way of knowing the size that user input will be. And because in C, you can do arbitrary pointer arithmetic, I can take this S and I can add stuff to it. I can call a function, I can do like the square root converted to an integer of some other value read by the user. And now, how am I going to predict whether this is within the string that the user defined or not within the string that the user defined? Very, very hard to predict at runtime in general for all programs. Not impossible. So not impossible in all cases, but if you assume that the programming language is a Turing machine, then Turing demonstrated, or at least Turing and Rice demonstrated that it's actually not possible in general to write a program like a compiler that will figure out in all cases for all possible input programs whether this is out of bounds or not. So if you're interested in that, actually, I have a program analysis class, a graduate program analysis class that you could take, not this spring, but the spring after, where we go into that a little more, how program analysis tools can still rule out some of these bad cases and do so for all possible input programs at the expense of rejecting ones that actually aren't buggy. So that's one way to do it, but you can also insert runtime checks. So somebody asked for debugging, is there a special compiler that has runtime checks? For C, that's a good question. I don't know. There are certainly tools. You can basically just use a new version of, so for heap stuff, let's see. That's a good question. Yeah, you'd have to use a new compiler. There are compilers. Let's see if GCC does it. Yeah, I don't know if GCC does it, but there are certainly compilers that will insert these runtime checks for you. There's all sorts of tools. I can't think of any that are like production right now, but I know there are research tools that will insert checks to do this. And in fact, there are techniques for inserting special values in the stack to make sure that the stack itself hasn't been blown away, because that's been such a critical problem for security. So I don't know any offhand that can do this, but I'm sure there must be some C compilers out there or some flags that maybe the GCC that you can add these runtime checks. But I'll leave it to you as an exercise to Google these and find these. I'm sure they're out there, but I don't know any offhand. All right, questions so far on pointers versus relative addressing in the Intel architecture. Okay, so just to show you, let's see if I can find this real quick. Yeah, I think as we look into it more, I mean, really, this is kind of, this is like overlapping with CDA a bit, and I don't want to get too much into just describing all of like assembly programming, first of all, because I'm not an expert in assembly programmer, but also because it's not really necessary to learn all about the way the assembly works. We just need to know enough to compile our programming language. And if you're a compiler writer, then you should know in detail the architecture so you can write optimal code and take advantage of the architecture as much as possible. But for our kind of simple compiler, we just need to know a few instructions to generate corresponding code for our input language. Okay, so this is, so before we take a break, this, and I've given you a reference in here to this guy's website, Felix Clodier, who basically, I don't know, somehow derived the instruction set from Intel's official documentation for their architecture, which is, as you can see here, a light reading at 5,000 pages long. He kind of summarized all the instructions here, and you can see there are an absolute, yeah, I'm being sarcastic if you can't tell. You can see this is why Intel is a CISC. Yeah, book report. Yeah, do a book report. Somebody asked if there's a book report on this 5,000 page reference manual. Yeah, it is. So one of the reasons why I'm not an expert in assembly, I'm more interested in the programming language than the assembly language. But you can see here that there are just tons and tons of instructions versus the RISC architectures, which have many fewer instructions, and you can almost, in a sense, compile the assembly language from a CISC architecture to the RISC instruction set. And in fact, the Intel under the hood writes these. Where is my move instruction? Under the hood, Intel is actually implementing these instructions using a kind of RISC-like instruction set called Microcode. Did you guys learn about Microcode in CDA? So this is the pseudocode of the Microcode. So those instructions, those CISC instructions, those complex instructions that Intel provides you, under the hood, the hardware designers at Intel actually implements those using yet another language in a reduced instruction set called Microcode. And that Microcode is much more like RISC architecture. So it's almost like you've got a bunch of RISC processors with an interface to them to implement the Intel, that whole big Intel architecture. And so this is some pseudocode for that implementation of these assembly instructions. And so I am by no means an expert in this, but it's, yeah. So I'll leave it to you to go over this and look at these. I'll show some of the simpler ones I can, kind of understand enough to talk about. But there's a lot of complexity in Intel, where they're supporting, some old memory addressing modes. They would have several special registers for allowing you to access memory beyond, 16 bits or 8 bits. And I think some of that is preserved in the modern architecture. Okay, so let's take a break for now. Let's reconvene at 11:30. So this was a lot to think about for assembly. Take a breather. Let's come back and let's look at pointers again and really drive home this point that why pointers work the way they do, and really how pointers are really just a register holding an integer that means a register location according to the developer, just by how it's used. Okay, so let's come back here at 11:30 and we'll look at that and project 3. So I'll be here for questions for a couple. Actually, I'll be back in a couple of minutes, and then I'll come back project 2 or whatever else. So I'll be back in Okay. Questions about anything? Can you guys hear and see me? Okay. Any questions? Final exam. That's a good question. It'll basically be content from the homework and from the projects on how to prepare. So I have not made the final exam yet, so I don't know. But we're going to have a review session the week before it. And as long as you can do the homework and as long as you understand how the compiler works, then you should be fine. I'm just going to ask questions from that. Probably very similar questions to the homework that you got, and yeah, just some details of the simple C compiler. Will it use honor lock? I don't think so. Yeah, I don't feel all that comfortable using that. Apparently, it requires a certain operating system, and is requires taking over your like webcam and stuff. Yeah, it seems like it does seem kind of invasive. So I won't do that. I haven't actually decided yet what the format will be. The final is the last day of the semester. Really? When is the final? 12:04? Oh, that's review. What am I saying? Huh. Yeah, it's 12. All right. Okay. The 11th. Oh, well, sorry about that. It's too bad. Yeah, I haven't figured out the format yet. I've never given a remote or a virtual final exam before, so I don't know how it'll work. Yeah, I don't want to use honor lock or any of those software, but I also, don't want people to cheat. I mean, of course. I don't know. I'm sort of deciding between having, I think Web Courses has these timed quiz type things, but it could also just do like a take home final kind of deal. Yeah, exactly. Yeah, that's one thing I'm thinking as well. It's like a take. I think do you guys still call that a take home final? We don't call that a take home final in math or whatever. But yeah, honor lock does seem a little. The amount of. Yeah, it does seem like a kind of. It seems like it requires a lot of privileges to do what it's doing, and I'm not entirely convinced of its. That it actually will achieve what it's supposed to achieve. That I'm not sure. Like I guess it just makes it harder to cheat. But I mean, I can't imagine you can just have a separate device open right in front of you. Yeah, that's what I was thinking. Using time could do it. So where on the time it's tough. So this is how the foundation exam works? This is what he did virtually. I should ask him about it. I should talk to Gua. He always has a really good insight on this stuff. He helped me a lot when I was started a couple of years ago. Okay, so the foundation exam went pretty smoothly. Yeah, so I'll see whether it's going to be like a take-home final, whether there's going to be notes allowed or not notes allowed, take-home final versus a timed thing to help avoid cheating. I mean, if it's I'll see. I haven't yet decided. So sorry to make it uncertain. That kind of procrastination is a good way to save time, sort of. Yeah. So somebody's saying they can't make a discrete final automata in 5 minutes. That's why I'm a little, because the foundation exam is a knowledge test to make sure that you meet the cutoff and you have the competency to continue computer science. Whereas in a course, it's a little bit more like a knowledge test, or like, can you apply those? I mean, I guess it's similar. I don't know. I guess it's similar. but also some things for this class require a lot of reference material. And so I either have to provide you all of that. I can't expect you to know the entire Intel instruction set or even the details of writing assembly code. I mean, I don't even know if I could do that. 3 hours to make our compiler backwards compatible with Java. Okay. So somebody's saying you display one question at a time. Yeah, it's a little. Yeah, it's sort of yeah. So some people like to do what they consider easy questions first and then save the harder ones, or come back to questions and check them. Yeah, so maybe a take-home final. Yeah, especially for this, because as you guys are implementing it, this is more like a slow burn, deliberative programming process, and so it does take a lot of kind of sitting and thinking and looking at the reference material in order to work out the solution. So somebody's asked, how do you check the pointer and Checkarray expression? I think we covered that at the beginning. You just recursively check the expression, the expression and array expression. You don't have to worry about what kind of expression it is. So somebody's asking, actually it might be kind of tough to Google this stuff. I mean, if you Google it, then one philosophy of exams is that they're a way to kind of push you to learn something. And so if you have to go search on the internet for like how to generate code that organizes the stack frame, and you looked on the internet to do that, you're not going to be able to just copy it verbatim. So you're going to have to like work out how the stack frame works, and then you've learned something. Oh, that's good. Well, I mean, by all means, Google some of these topics, especially for like, Intel assembly and how the Intel AVI works. All this stuff is public information, and for curiosity, it's okay to Google. So somebody asked which project is going to be the most difficult. Yeah, that I don't know. We'll see with the code generation to see. We'll see. Wait, you can see how code generation is. Yeah. So somebody mentions about learning versus grade. I mean, to me, the grade is. I think the main problem is like security of the grade. The grade should have some meaning. Ideally, it should have some meaning, but that meaning should really be. Depends on what you think that meaning should be. If you tie like people's future careers to it, then you're going to incentivize gaming of that grade. But ideally, the grade is a reflection that you've learned the content and have the whatever competencies are meant to give you in that class. Yeah, the simple C stuff, I don't think you're going to be able to Google that. So how that compiles, and if you need to use the reference manual, these project descriptions to see how to compile it, then you're just doing what the question is asking anyway. So yeah, I mean, talking with you guys, maybe I'm leaning more towards this take home final. Maybe that's easier. I'll see. Or maybe it's like, 5 hours or something where we don't have to proctor it, and you guys just do it on your own. So maybe not 24 hours, maybe it's shorter. So maybe that'll minimize the unethical cheating that some people will inevitably do. But yeah, the Guha's approach. Guha is very good at this stuff. So his approach of putting a time constraint on it to at least make cheating harder is an interesting approach. So we'll see. We'll see it in a little bit. I have to also write the exam, figure out the exam and try to time it, get the TAs to take it to check the time. All right, glad to hear you like the assignments content so far. Hopefully everybody's sort of getting it. I'm trying to make this much more intuitive than before. Okay, so I'll see how it goes with the exam. Depends on how large it is, how much time you need. I'll try to calibrate it using the TAs as guinea pigs before that. So I just dropped this on the TAs right now. they probably were not aware of this till now. All right, so it's 11:32. Let's get back into the content of this course. So we left off talking about how pointers work at the assembly level, and really why pointers exist. Because you have these different addressing modes, you have these different ways to move data around your actual architecture. So as you guys learned in CDA in architecture, the processor itself has some memory storage on chip, the registers, which are really fast to use, much faster than having to go out to the memory bus and read and write memory from RAM. RAM is really fast, but it's not, doesn't even compare to doing register access. And so assembly developers, in order to squeeze performance out of their devices, would consider the difference in time and also the caching behavior of the architecture to make sure that the code they're writing is really fast. And the registers, at least in a RISC architecture, the registers are where you do all of your computation. And if you need to access memory, there are separate instructions for doing that, like load, and store instructions. In the Intel instruction set, because it's this CISC architecture, there are instructions that combine many individual operations on the processor. And so the process of accessing a memory address, you may have several instructions to say, well, okay, get the memory address and get the data that I want to store in that memory address, then call load. In Intel, you can do these with, at least in the assembly file, you can do these with a single mnemonic, a single move instruction, and just give different operands to say whether you want to move between registers, whether you want to move to memory. And they also have these fancy addressing modes that allow you to do offsets of these memory addresses. And this is really where array indexing comes from in C. So in this example here, where we're accessing the memory location at a given register, in this case, RBX holds a memory location, these parentheses in the AT&T Intel syntax says we want to move the contents of RAX to the memory address stored in RBX. And that's exactly what in C we do with this assigning to a dereference of a pointer. Okay, so questions on that so far, this notion of this relative addressing. So not only is that used for arrays, the compiler takes advantage of that fact to, so that the parentheses signify that it's an address instead of the actual value of it. Very, very terse, kind of esoteric syntax, but this is the AT&T syntax. And when you want to do an offset, you put the offset before it. I mean, actually, I think you can swap these things too as well. I don't think the assembler cares whether this is a constant or an immediate, which they call in the assembly world, versus a register. This is AT&T syntax versus Intel syntax. Okay, and so the compiler takes advantage of this to implement functions. So functions are implemented because as we now know, hopefully, that the architecture itself doesn't really support the notion of a function the way we think of it in programming languages, where it has its own state and you freeze that state and go off and run. You can go off and run other functions. You can recursively call it, and it's actually a new instance of the function. The architecture doesn't directly have instructions for that. Instead, the compiler keeps track of a function's memory called a stack frame, and always maintains one register. So there's a limited number of registers in any processor's architecture, and it's devoting an entire register just to hold this stack frame and the pointer to the stack frame. It holds the memory address of this stack frame. So a pointer is just a register that holds a register or a memory address that itself holds a memory address instead of an integer. And at the architecture level, they're just bits. There's no distinction at the architecture level with what's stored in memory or register. It's really just because we use it as a memory address. And that's also why you get a segfault, for instance. If you try to dereference the null dereference, that's because you're trying to access the memory at address 0, and address 0 on most machines, at least most operating systems, or at least desktop operating systems, is protected from writing by the hardware. So somebody's asking register 31. Well, the registers in okay. So register 31. So this is from like the RISC architecture where they number the registers. In Intel, the registers have different names, but it's the same idea. You can also just enumerate them. In the Intel architecture, there are these special purpose registers. This is what one of the features of RISC versus CISC, where CISC you have special registers. I think some RISC architectures also, they'll either have a convention where a certain register is always the base pointer, for instance, or always the stack pointer. But it's the same idea. So there's no register 31 or no register 0 in Intel. Instead, they have these registers named like this. There's a reference in Project 3 if you want to learn a little bit more about the different registers in Intel and the history of it and why Intel, for backwards compatibility reasons, names the registers the way they do. There's a link here to the x86 register meaning and history. So just as a kind of a brief overview, the original Intel processor, the 8008, gave letters to the registers. That was just their convention. And they were 8-bit registers. And when they moved to a 16-bit architecture in the famous 8086, which is, I think is even, this architecture may still be used for like, traffic lights or something like this. When they made in 16-bit registers, they still allowed you to refer to the first 8 bits, or the 8-bit halves of these registers. This was just design. A RISC architecture, I don't think, has this. The RISC architecture may have a way to get access part of the register, but in the Intel architecture, you can refer to the first 8 bits or the last 8 bits of a register using AH and AL. And so the 16-bit registers were called AX, BX. They put this X prefix at the end when they moved to 16-bit. Several years later, they moved to a 32-bit architecture, the x86, and they did the same thing. And they kept these old register names, and you could refer to those old registers. You could still refer to them in your assembler, and the assembler would produce the right opcodes and to refer to those. And then the 32-bit registers were prefixed with E. So E, I don't know, enhanced, extended, who knows? So now the 32-bit registers was EAX. And as it says, wait, there's more. Once they came out with the 64-bit architecture, which actually AMD came out with, they beat Intel to the punch. And actually, I think they designed, so AMD was would make Intel clones. They would try to support the same instruction set at the interface level, but they had their own architecture, proprietary architecture designs that implemented it. They were like, we're coming out with 64-bit first, and they became like the standard, basically, from what I understand, for 64-bit Intel architecture. And they did the same thing. They took this same EAX register, and now they have RAX for the 64-bit register. So if you reference the EAX register, you're getting the lower 32 bits of the 64-bit register. So even if in the assembly you're referencing a different register, they are if you copy data into RAX and then access the data in EAX, you're going to get the lower bytes of whatever data you copied into RAX. So somebody said, will 128-bit be a thing in the future? I guess so. I actually don't know. I don't follow the hardware news that much, but you can look it up. I think there are, okay. So the really actually what kind of took over, not just 128-bit, but like entire vectors of data and memory were GPUs. So GPUs, so I don't know if there's going to be a 128-bit AMD. I mean, maybe there is actually. There actually might be already. But really what took over not just larger bit widths, but also vectors of bit widths for doing statistical and graphical computation was GPUs. And so GPUs became not just something for, really cool gaming. Turns out that really cool gaming requires lots and lots of vector operations. And so those architectures were designed around really fast vector computations. And so that, people realized that you could apply that to doing statistical compilation. There's a lot of statistical work where you can just basically do matrix manipulation. And then, of course, statistical computation is the foundation of modern AI, machine learning. And so GPUs, one of the big revolutions in machine learning was using GPUs to do really large scale, really fast machine learning training. And so GPUs, I think, also kind of are the GPU and the CPU are like you equally important almost in today's computing. So let's see if there's a 128-bit. I don't know if Intel has come out with a. Let's look on Wikipedia. I don't know. Maybe they haven't released one. I'm actually not sure. But you can see the history here. But I think GPUs have really taken the helm of computation on large scale. Also, floating point operations. Also, GPUs are optimized for that as well. I mean, the Intel architecture also has floating point built into the hardware. Okay, so good questions. Yeah, machine learning, the machine learning version, which is really kind of the statistical AI. It's been around for decades with the neural nets of, like the 60s or 70s. There were these very simple neural nets. And actually just last year or 2 years ago, the Turing Award was given to Jan LeCun, Gregory Hinton, Yoshua Bengio for this machine learning based AI and the really just explosive advances in that, not just the scientific advances, but the huge impact that they've had on computing. And Hinton and LeCun were doing this in, the 80s. LeCun was doing this. LeCun was teaching at my grad school alma mater when I was there. I got to take a course with him, and that was like just before it like exploded. So I'm sounding like a little bit of a hipster here. I was there before it exploded. But he was doing this stuff in the 80s at like AT&T, doing like handwriting recognition. They had released products where they were like doing check. When you write a check, they would use this machine learning techniques all the way back in like the 90s to automatically read handwriting on checks, and doing a really good job of it. And once GPUs, and you can actually watch the lecture by LeCun and Hinton. Once they started using GPUs for it, they could do just massive scale. So they knew that you could do this sort of massive correlation, basically statistical correlation with these machine learning machines. But once they got their hands on implementing these on GPUs, where they could just do massive, huge data sets and massive training, then you start seeing, this crazy stuff from Google where they're like doing just very sophisticated, very higher precision matching of images and other kinds of more continuous data, like pictures, and treating words as vectors, like continuous style data versus discrete. But anyway, yeah, that you can go look at the whole series of that. I recommend watching the Turing Award lecture that Hinton and LeCun gave. Bengio, I don't know, for whatever reason, he didn't give the talk as well. But those three got the Turing Award 2 years ago, which is like the Fields Medal or Nobel Prize for computing. Okay, that was a big aside. So 64-bit, and this is the history of the naming of these registers. All right, so questions on pointers and this kind of relative addressing at the hardware level? Okay, let's get into our project, the project that's due. So it's due in 2 weeks, and it's to implement function calls and definitions, implement variables, and implement arithmetic expressions. We'll leave handling pointers in the language for the next project and handling control flow for the next project. So even though we're not going to be implementing pointers in simple C, we still need to understand the notion of relative addressing and memory addresses in registers in order to implement our compiler, because we use the stack frame offsets in order to store our local variables. Okay, so let me start with, let's see where to start. So last time we went over the function call ABI a little bit. Okay, so should I review that in detail, the function call ABI stuff, or should I just move on to arithmetic expressions and other part and variables? Who would like to see some review of the the prologue and the epilogue and passing parameters, passing the return value? Okay, let's do a review of that. So here I've written pretty detailed instructions on how function definitions get implemented in the compiler. Let me get the code for this. So I've given you the code for main, and as a little hint, remember that the main method is basically just a special function definition that has a fixed name and doesn't take any user-defined parameters. Here on the right is annotated code for generating the main function definition. So it's a little intense. So let's just step through it and see how we generate a function definition for C or simple C. So the first thing that we need to do is create a scope. The scope is where we're going to hold where to find the variables in memory. So just to kind of make it explicit, variables in a programming language are backed using addresses in RAM, typically, with the compiler. Now, modern compilers are very smart about making sure that those values stay in registers as long as possible. But generally speaking, variables are a way to name memory locations. And so in order to keep track of which memory locations variables correspond to, we use yet another symbol table. So the symbol table, instead of storing a type, now it's going to bind a name to a place in memory. And we'll see how that place in memory gets managed. It's going to be an offset from the base pointer. But just think of it as storing where to find that memory, where to find that address in memory. So the compiler can remember that when it's reading and writing those variables. So just some assembly stuff to get out of the way. We watched the last lecture. There's different sections in the binary file. So there's some information that we need to give the compiler. We need to give the assembler. We need to tell it we're in the text segment, which is the compiler. Yeah, in the toy compiler there were templates. Here we don't need them. Here we're going to be generating we're going to be generating those. They're called pseudo ops in assembly. We're going to be generating these, so we don't need a template for this version for this compiler. So we just need to tell the assembler that this is the text segment, which is where the code is stored. We tell it that there's a global symbol being defined here, and we tell it that it's a function, that global symbol is a function. So don't worry about this too much. I'm no expert on assembly. You can certainly look up sudo ops in the GAS, the GNU assembler. And then in order to be able to get the memory address of this function, we use a label in assembly. So the assembler will take care of the memory address for the function for us. All we have to do is give it a label. The next thing we need to do is look at all of the local variables, and I'll talk about how we do that in a second. But the local variables don't actually correspond to any, or the declarations don't correspond to any code in the assembly. The declarations really just tell the compiler that these are the symbols, these are their types, and the compiler just needs to make sure it keeps track of these in memory. So it doesn't have to do anything strictly to generate code for this. It just has to keep track of how much space it needs in the stack frame to deal with this. So recall in our stack frame layout, this is the runtime behavior of the program, but what the compiler does is it just makes sure that it emits code that will move the stack pointer ahead so that at runtime, it'll have this space for the variables. And I'll show what the output looks like, and we'll trace through it and everything with a debugger. But from a high level, all we need to do for declarations is we don't actually emit any code. It's really just, it's almost like hints to the compiler to say, hey, I'm going to use this symbol. This is its type. This is what its bit width is going to be implicitly, because each type has its own bit width. And so the compiler's job is to take all those declarations and make sure it emits code that allocates space for that at runtime. So remember, the compiler is not managing the compiler is not actually executing the stack, the changes to the stack. It's emitting code that at runtime will have the right behavior. It'll increase the stack pointer for us when that output program is run. So that's, that if you go back to the toy compiler to see this distinction between the compiler translating the program versus the assembler and the machine actually running that program. Okay, and then we need to make space for parameters. So just as an example, I've given you how to use my API to allocate space for the parameters here. So all you have to do to use the table is call insert offset, give it the current scope, give it the string name of the identifier, and give it the amount of space in bytes of an offset you want to give it. So for simplicity in the required project, everything is 8 bytes, both pointers and integers. If you want to get very fancy and you want to do some bonus work, take a challenge. The bit width of each symbol depends on its type. So a character is 8 bits, a single byte. Integer should be 32 bits or 4 bytes, at least in x86 64C. And a pointer is 64 bits or 8 bytes. But for simplicity, that means anytime you're doing any kind of operations on data, you have to basically look at the type of the symbol, look at the type of the operator, and use the correct register. Use the correct register. So that's a much trickier exercise to do. So I'll leave that as a challenge and leave for you to think about. But the basic idea is that the type checker is actually integral to code generation, because not only does it tell you what symbols that the compiler needs to manage at runtime, manage emitting code to manage it in memory at runtime, but it also affects what the operations that are going to be used. For different bit widths, you need to use different operations. If it's a floating point versus an integer, there are different instructions at the machine code level for different for whether you're doing floating point representation arithmetic versus integer representation arithmetic. Okay, so we need to allocate space, or we need to update the symbol table for the parameter. And remember, there will always be one parameter to every function. So that's one simplification of this exercise. You don't have to worry about all of the parameters that you can have. So there's only one parameter. It's always passed through a register. And that's described. That's described here. Oops. Okay, and so the next thing to do is emit the prologue. So if you recall that the prologue from last time will save the old caller's base pointer. It will make space for the parameters and local variables, and it'll adjust the stack size. And so I've done a lot of the heavy lifting with managing the offsets for you. So this offset table, this offset scope will also keep track of how much space is needed for all of the parameters and locals that you've added. So when you call insert offset inside of decal list, inside of the code generation for decal, and when you call insert offset for the one parameter that you need, the scope will automatically manage the offsets for you. So all you have to do is tell it the identifier and tell it the size of the data for that identifier, and it'll manage the scope for you. Yeah, so I left bit width in there. So this is for people who want to do the bonus exercise. So I left this in there because it tells you what the bit width of each type is. But for the simplified version of the project, simple C, all you have to do is assume everything is 64-bit. So we emit the prologue. We move the parameter registers to the stack. So why is it that RDI holds the parameter, the first parameter? Why does RDI hold the first parameter? Why can we assume that? Any takers? I'll leave a hint here. Yeah, exactly, convention. So it's not even, it's partly an Intel convention and partly an operating system convention. So yeah, it's the ABI, the application binary interface. Just by convention, we put the first parameter in RDI. So when you write your code generation for function definitions, you can assume that there's always one parameter and only one parameter, and it's an integer, a 64-bit integer. So all you have to do in your implementation of function definition is always move that one parameter and push it onto the stack. Okay, so the function prologue will set up this part along with its local variables. Let me get back to the thing here. Wait a minute. This code is wrong. I have to fix this code. I will send out an update and announcement. So really what you need to do is, where's code gen? Decal. I'll make this more clear in the instructions what you need to do here, but you need to look up the offset and move RDI. So this really should be move RDI into the offset, but I will give you better instructions in here for this. I'll give you that. So I just noticed a little mistake here. So sorry about that. I will give you instructions in the project 3 for that. But basically all you have to do is look up the offset of the first parameter, which is lookup. Do I have an example of this? Yeah, so you basically do this. You basically have to do something like this for moving the RDI into the right offset. Okay, but I'll give more details in the project. Okay, somebody said this looks somewhat similar to the type checker, and that's exactly right. So these are just traversals of the AST, basically. And so the type checker is almost, in a sense, kind of interpreting the input program, but just in terms of type values. Like if you think of types as values of variables, then the type checker is kind of running the program, but running it to compute the resulting types of each operation. For code generation, we're not running the program, but we're generating equivalent code for each of those constructs. So for both of them, we're going over the abstract syntax tree, which holds the the constructs and hold each grammar construct of the input program. And we're either interpreting or translating that code based on it. So it will look very much like the type checker. And in fact, the code generator also has a symbol table to keep track of offsets, just like the type checker has a type checker, but to keep track of types of symbols. Okay, yeah, so the comments, somebody asked about the comments. I put them in there so that the output program will have, it'll comment the sections of assembly so you can see where they came from in the output program. And then we just call the function to generate code for the statement list. We call the function to generate code for the return expression. And then we save the return value into RAX. So why do we use RAX for the return value? Right, exactly. The Intel convention is to return the value in RAX. So somebody asked, won't comments make diffs not work? So we're going to diff we're not going to diff the assembly output, because there are many ways to generate the output. And as we saw with the toy compiler, it's a pain to, with white space to get that right. Instead, we're going to compile your program with your simple C compiler and then run it and see the output and check the correctness that way. And so I'll show you how, so the main, as you noticed in C programs, the main function has a return at the end, and that return actually goes to the operating system, as we talked about, I think, very early in the semester. And I'll show you how we can inspect that value. Okay, so this is a good question. How can we pop RAX? So hold that thought for a second. So this is the convention I'm giving you for handling expressions. So by convention, anytime you call CodeGen expression, the interface that the compiler, the internal interface of the compiler, is that we can always assume that expression pushed the resulting value onto the stack. So this is because, as we'll see with expressions, when you're computing an expression, there's a bunch of intermediate values you need to hold on to while you're computing the expression, and those may exceed the number of registers you have in your machine. So at some point, you're going to have to put these into memory. So the simple way to do this is to just hold those values onto the stack, and we'll see that this works out really nicely with a tree traversal of the expression. Okay, so the last thing we need to do, so hold that thought, I'll get to expressions in a second, and then the last thing we need to do is emit the epilogue, which destroys the stack, restores the base pointer for the caller. And then just destroy the scope. So in this simplified version of the program, there's no nested scopes. You don't have to worry about global variables or anything. So there's really just going to be one scope at any given time, the function local scope. Oh yeah, so Josh points out that we're not just going to look at the return value. We'll look at the we may look at the whole output of the program, but we'll see that later. We'll see that later how it's going to be graded. So yeah, so there's no global scopes as well, because with global scopes there's a different way to access the variable, the value, the global value. Instead of doing an offset from the base pointer, you need to get the offset into the data segment of the object file. So global values global values are something that get a fixed address. So unlike function local variables, which are relative to the base pointer, global variables are actually fixed at the top of the data segment, or at least fixed for one run of the program. And there's a little trick in Intel where you access it as an offset to the current instruction to get to it. But we're not going to have to worry about that in this simplified version of the program. So somebody's asking, are push and pop operations adding to the stack beyond the stack pointer? That's right. Yeah. So when you do push and pop, the Intel architecture says that the stack pointer gets incremented and decremented, or decremented and incremented really. They get modified when you do push and pop. So if we look at push,
the microcode for push, well, first, it actually looks at the size of the address, but it will, if you do a push, it'll first move the stack pointer and then do the memory move, basically do the store to the stack pointer address. Yeah, so somebody's asking, the push and pop in one scope cannot be used for another scope. That's exactly right. But as we'll see, it'll actually work out, because if we call a new function or have a new scope, that epilogue pushes a new stack frame onto the stack. And so whatever was on the stack for the caller will be held in that stack while the callee does its work. And once the callee is done, it'll destroy its stack. It'll move the stack pointer back to what it was before the function was called. And then it's as if we never left the function in the first place, at least in terms of the stack. So that's why this trick kind of works, because we can do whatever we want with the stack within a function, because we know that if we enter a new scope or we call a new function, that we're going to have a brand new stack frame added onto the end of the stack. And we know that we're never going to have to access the caller. For a function call, we're not going to have to access the caller. And so there's no need to worry about what the state of that stack was before we called our function. For compound statements, a little tricky. So this is one thing I also left out of this project. For compound statements, when you have nested scopes, you need to still be able to access the parent. And this is the same for global scopes. And if you have nested functions, like some languages have nested functions, you still need to be able to access the parent scope. And you do this by following the stack of base pointers. So the base pointer points to the previous, the base pointer that you pushed into the stack frame points to the previous function's base pointer, because you need that in order to get back to the base pointer. And you can follow the chain of those to find parent scopes data. This is detailed in the Dragon book, so you can take a look. Last time I gave readings in the Dragon book, so you can see details of how you follow that chain of stack frames to find parent scopes. But you won't have to implement that here in this project. Yeah, so there's tons and tons of stuff in compilers, and maybe in a graduate compilers course we could get into a lot more of these details. But for our purposes and to make the project simpler, you don't have to implement this. You don't have to implement these complexities. Okay, so somebody's asking, don't you need nested scopes for compounds and while loops? So yeah, the full simplicity language allows this, but this is what you'd have to do. You'd have to make effectively give it its own kind of stack frame. I mean, there's many solutions for handling nested scopes, but one way to do it is to just like a function, have a nested stack frame. I have another stack frame for the compound statement, and that's how you do it. But I'm just saying you don't have to do this for the project. The simplified language will have no local variables within compound statements. There'll be no nested scopes that you have to manage. But for the full language, you would have to manage the state stack for that to give space for those nested local variables, and also be able to look in parent scopes for the offsets for variables. So just to, since someone asked this, just to point out what I mean by this, if I've got an if statement and I have y and I assign y to x, at the assembly level, this is stored relative to the parent scopes. Well, this is stored in the parent scopes stack frame. And I want to read that value or write that value in the child scopes stack frame. So in order to translate these to assembly, I need to know the offset from the parent. And so to do that, you follow the chain of base pointers that are pushed onto the stack. So recall that the epilogue of the function first pushes the old functions or the old stack's base pointer. So somebody's asking the main references to use for this assignment. Yeah, so just like the type checker, it's the same as the type checker, except instead you need the you need the project 3 reference instead of the type specification. But it is in a lot of ways very similar to the type checker. You're kind of interpreting the language, but in this case, we're interpreting it by saving offsets in a symbol table and then emitting code for each of the instructions. So let me actually draw a little diagram of how this. So even though we're not going to have to implement it for this project, you can certainly implement it as a bonus exercise. But let me show you how these nested scopes work at runtime and how the compiler generates code for these nested scopes. Oh, okay. All right, so I'm going to draw my stack frame growing down as it does in the machine. Let's get some code here. So if I've got a function f, it defines variable x. I've got an if statement that wants to it defines its own local variable y and assigns x to y. Questions on this example? Everybody knows the meaning of this, right? So somebody asked, you could use this with the symbol table. It's just because you're binding to a different thing. Instead of binding to a type AST node, you're binding to an integer for the offset. Okay, so here's our example. At the higher address in this stack, we have the stack frame for f. So this is f's stack frame, and its stack frame, has the return address that for its caller, and it also has the base pointer of the parent stack frame. For this nested stack frame here, so that we can think if there's many ways to implement this. So GCC does not use a new stack frame to do this. GCC will go through and figure out all the possible local variables and allocate them once. But if we want to use this technique where we have nested scopes, and we have to do this for nested functions as well. If we want to see the technique for nested scopes, what we'll do is we'll create a new stack frame for our nested scope. So this is the ifs scope here. And the first thing it has in its stack frame is the old base pointer. So when I'm inside of this function here, and I have my stack frame to the function here, where does RBP point to? What address does it hold when I'm executing it? When the function is executing, what RBP does it hold, or what does RBP hold? What is it pointing to? Does anyone remember this? I can show the Intel ABI if you want a refresher. What does the base pointer hold? So recall that where is it? So recall that the base pointer always points to the current function's stack frame. So in this case, when we're executing the function before we enter the nested scope, RBP has the address of this function's stack frame. Right, the return address is right above it. And what's after the return address is the saved base pointer. So that's the base pointer of the caller function. So remember, if you recall, when we call a function, we don't want to lose track of all of the state of that function. And so in order to be able to restore the old, so the base pointer, we have to update the base pointer for the new function, but we don't want to lose track of what that base pointer was for the caller. So we store the old base pointer we save the old base pointer in the stack. It just so happens that we update the base pointer right after storing the old base pointer. So it happens to be for the convention that the current base pointer is actually always pointing to a memory location that holds the old base pointer. That's just by convention. I mean, strictly speaking, this whole thing is the stack frame. But by the way, the convention creates the stack frame, the new base pointer will point to an address that holds the old base pointer. And it turns out that actually is not, that's actually by design. That makes what I'm going to show you now a little bit faster to do. So it's just by the convention, the old base pointer gets pushed, right after the return address, and then the new base pointer gets updated immediately after pushing the old base pointer. Okay, so that's how the F was called. When we enter this new scope, or we enter a new, nested function, if we enter a new scope, the one way to do it is to make a new stack frame. And the first thing we do for the new stack frame, we don't need a return address because this isn't a nested function call, it's just a nested scope. The first thing we do is we save the old base pointer and update the base pointer to point to our new stack frame. So then when I've got a local variable here like y equals 2, I make an offset in the stack frame to hold y, just like a local variable for the function or a parameter for the function. Okay, so here's a tricky question. What would the assembly code look like? What would the assembly code? Yeah, so registers are finite. There's like 32 or 64 or whatever. What would the assembly code look like for assigning y to 2? So it's going to be a move instruction. So let's say we're just assigning 2. So it's going to be a move instruction. So remember, this is the source. Somebody's already got it. So somebody said move 2. Well, we need a money sign to say it's an immediate in AT&T syntax. Move 2 to -4 RBP. So -4, assuming, it could be -4, it could be -8, depending on whether it's a 32-bit or 64-bit. Well, no, actually, in this case, so RBP is 64-bit. So it'd be -8 to move past the RBP. Well, okay, so let me show how this is working. So this is saying move the immediate number 2 into this address. And if you recall from the first half of the lecture, what this address means is it says go to RBP, get the value of it, subtract 8 from that value, and then load or store this number into that address. So get the address inside of RBP, subtract 8 from it, and then store whatever this operand's value is into that address. So, okay, so let's see why it's 8 bits. So let's see how this works on our stack frame here. So when we created our new stack frame for this local scope, we immediately pushed the old base pointer. So that was the first thing in our stack frame. And then we updated the new base pointer to point to this address. So I'll show this when I step through the debugger will help us see the actual addresses here, but it's a little tedious to write this out and show it. But this is some address here in memory, and RBP points to it. So if this were just RBP, we would get the address of the old RBP, and we'd overwrite this value overwrite this slot in the stack. By saying -8, we move 8 bytes past this slot in the stack. The reason it's 8 bytes is because pointers are 64-bit, which are 8 bytes. So because the current slot we're pointing at is the old base pointer, we move 8 bytes down to now have the memory address of this slot, which holds Y. And so that's how, so great. Yeah, so you guys got the right idea though. We take the operand here and move it into the relative address, the register relative address here. Okay, questions on this? You guys with me so far on this? How we access an offset from the base pointer in order to access local variables. So at this point, yeah, so depending on the size, so somebody asks, what would the stack pointer be right now? So once we push this, the stack pointer is here. And once we make space for this local variable, the stack pointer is, this is the top of the stack. Oh no, wait, I'm sorry. The stack pointer, I have to remember the Intel microcode. Stack pointer is here when we push RBP. And then when we call push again, it decrements the stack pointer. And then, so it points to the last element, or the top element on the stack. It doesn't point past it, it points to the top element on the stack. So the stack pointer would actually be here, would actually be -8 from the stack pointer. But if we pushed another element, then the stack pointer would, well, okay, let me put the offsets here. So this is an offset of -8. And depending on if we had another variable here, this offset would depend on the bit width of Y. So if Y is a 4-byte number, then this would be 12. The offset of Z would be -12. If it's an 8-byte number, the offset would be -16. If it's a 1-byte number, and so on. And so actually the offset of this number doesn't include its own bit width. It includes all of the widths of the elements on the stack before it. So that's a little tricky gotcha to get right when you're looking at these offsets. Another thing to keep in mind is that I can't remember the details about when this actually happens, but I think compilers will actually align these stack elements to be at 4-byte boundaries or 8-byte boundaries or something. They'll actually, instead of allowing a single byte to be pushed onto the stack, they'll align these at 4 bytes anyway. I think the push and pop in the Intel architecture works on 64-bit numbers anyway, 64 or 32-bit numbers. So I think that's why our compilers will generally align these to 4-byte boundaries or 8-byte boundaries, depending on the design. So you won't really have an offset that's like, -9 or -32. It depends on what the compiler does. It depends on the architecture. But okay, all right. Questions on the stack frame and accessing elements in the stack frame. So for those machine level details, take OS or look into like a real compiler, read the GCC documentation, read the Intel stuff. Not my area of expertise. So if you're interested in it, take a look at the specifications or look at compiled code from GCC, and you'll see these extra instructions for like aligning, doing alignment and stuff. Okay, questions on accessing variables from the stack frame. All right, now here is the tricky part. How do we access X? So I'll give you the first part of this instruction. We're going to move whatever is in the memory location that stores Y into something. So this is a little bit of a trick. How do we store something into X? So remember, we're according to the rules of our language, we're allowed to access X because our definition says that we can access any variable in any parent scope. Given this scheme where we use a new stack frame, how do we access X? What do you guys think? This is definitely a tricky one, and I wouldn't necessarily expect you to know exactly how to do this, but let's take some guesses. How would we access this data. Good. Use the old base pointer. So this is exactly why we store the old base pointer, not just because we want to restore it, but it also allows us to access the variables from a parent scope. Now C does have nested functions, but I don't think it works like this. Some languages have nested functions where you can access the parent scope, like Pascal or Ada languages you actually may have never seen or heard of. But those languages actually have nested functions where you can access the scope of the parent function. Similarly, by implementing nested scopes using this stack frame trick, it's not the only way to implement them, but if we use this stack frame trick, then the way we access parent frames is with the old base pointer. The old base pointer is the first thing we pushed onto the stack when we enter the scope. So we want to have a relative offset to this old base pointer. So let's pretend that we've gotten that old base pointer inside of, let's say we put it in the AX register. What would the offset be for X? So we have to do, how would we, say RAX holds the base pointer for the parent scope. How would we fill in this operand to access X? Good, yeah, -8. So if RAX holds the old base pointer, then we access it just like we have any other base pointer, our current base pointer. But what about RAX? How do we set RAX to be the old base pointer? This is going to require a little bit more puzzle solving to do this. So someone says move our BP, I think you meant, into our AX. So let's take a look at this. This says go to the address at the base pointer, get that address and move the value at that address, which holds the old base pointer, and move that into the RAX register. So now the RAX register holds the address of the old RBP. It holds the value of this stack frame, or the stack entry, which had the address of the old base pointer. And now that RAX points to here. RAX now points to here, what the old RBP was. And by doing -8, now we access the local variables of the parent scope. So that's exactly right. We dereference the current RBP to find the old RBP and use that to index into the parent stack frame. So somebody also asked, do we move it into RBP? So if we do that, then we blow away the current base pointer. We have no storage in memory about what the current base pointer is. So then that will work. But if we continue on processing that function, any other accesses to local variables and the return value we've lost that. We've lost track of that. The runtime program now no longer has a way to return. Well, so somebody asked, shouldn't we use RBP as the offset? So if you look here, instead of using RBP for the parent, we moved the address of the old RBP into RAX and then did relative addressing from that register. So RAX has now become the value of the old RBP. So this is a little bit tricky to work through, but this operand here, this is the value of Y. So this is Y. and this is X. So we access Y using the current base pointer because it's in the current scope. And we access X using the parent scope's base pointer, which we get from the current scope's base pointer. So somebody's asking why for assigning to, oops, confusing myself here. 2 goes into Y. So somebody's asking why move 2 into, puts the value offset the new base point for the old. So one thing I didn't make explicit here is that this is sort of from last time. I'll step through this in some real code. But when we create this, well, okay, actually it's here. When we create this new stack frame, the first thing we do is we save the old base pointer and then reassign the new base pointer to be pointing to the new stack frame. So that's why move 2 into this offset from the base pointer worked on the new stack frame and not the old one, because the very first thing we do in constructing our, in our prologue to our function is to save the old base pointer and create and update the new base pointer to point to the new stack frame. So it's a very kind of subtle, I mean, the convention is designed very subtly with performance in mind and ease in mind, so that by the time we get out of the function, all we have to do is trash the stack pointer, make it point to the current stack pointer, which trashes the stack. And then right at the top of the stack is going to be the old base pointer, so restore it. And then the next thing that's going to be on the top of the stack is going to be the return address, so that you can get back to your old function. Yeah, so somebody asked, doesn't RBP, in parenthesis, give the content of where that register points to, and given the old RBP address? So that's exactly right. So that's the whole point of this, is that the point of this is we want the address of the old RBP, because that's where X, so I didn't actually write it here, but that's where the local variable for X is stored on the stack. So we want to have the old base pointer. Yeah, sorry. So I didn't put the X there. I just put the X. Somebody asked about this. So this is why we get the address this is why we get the slot here, the old RBP slot, because we want the address. Yeah, so RBP doesn't equal 2, but parenthesis RBP, minus 8 RBP, this equals 2. So yeah, so this is good. You guys are already moving ahead. So after I run this code, both Y here equals 2. This puts 2 into the slot for Y, and this puts 2 into the slot for X. And somebody confirms that if I put -8 with the offset to, well, no, -8 from the RBP gives an offset into the current stack frame. -8 into RAX gives the offset from the old stack frame, because we pulled out that old stack frame's address from the current stack frame. So that's why X is referenced using RAX here, and Y is referenced using RBP in this scope. If we were in the parent scope, we'd access it using RBX. Okay, so I think you should rewatch this, work it out on paper. No, RBX, so recall here, RBX does not point to the old stack frame at this point in the program. RBP points to the current stack frame. So since I'm going to show this anyway, let me show some of the assembly code for an example function. It's not going to have the nested stuff, but it will at least show you I'll show you what the prologue looks like. And hopefully this will drive home last week's lecture a little more when I show you the prologue. So here's a function f. Don't worry about what the function does, but this is the prologue of the function. The very first thing it does is it pushes whatever the current RBP is. So the invariant of the compiler that it enforces that RBP always holds a pointer to the stack frame, the address of the current function stack frame. So when we start running a new function, the very first thing we do is we save that base pointer onto the stack frame, onto the stack, and update the current base pointer to be the top of the stack. So that's why we get, that's why our stack frame looks like this. Yeah, the prologue sets it up by saving the old base pointer and then immediately moving the stack pointer's value into the base pointer. So when we push RBP, it updates the stack pointer to point here, and then RBP gets the value of the stack pointer. So right now, both the stack pointer and the RBP have the exact same address, and their addresses are both this stack frame entry. And as somebody is already asking, the epilogue tears that down by blowing away, you know, restoring the stack pointer to what it was before we called it. And so this, I mean, it's this very like subtle, low-level tricks here that have been developed over years and that have been baked into the convention. But we restore the stack frame by taking the current base pointer and setting it to be the stack pointer. So if you remember, when we created the stack frame, when we first created the stack frame, at one point the stack pointer and the base pointer had the same address. And so once we get rid of all the local variables, now well, anyway, we don't have to do that. But the point is that the base pointer in the prologue was set to be the stack pointer after pushing the base pointer. I think you need to step through, I think I need to step through because it's confusing to say, but it's basically the reverse of what we did in the prologue. In the prologue, we push the base pointer and then update the base pointer to be the stack pointer. And then when we reverse that, we update the stack pointer to be the base pointer and then pop the old base pointer off the stack into the new base pointer. So this is overwriting the stack pointer. This is overwriting the base pointer. I think this is much easier to show while walking through. So let me actually just do that now, and then it'll show you how how to use GDB, and I think we'll have to go over. So I'll do what I usually do. We'll end at 12:50, but I'll continue recording to go over expressions, and the next time we'll review expressions. You know, it's described in the document, but we'll review expressions. So let's take 10 minutes to look at GDB and stepping through the program, because I think that's going to be important to help you guys debug. And then I'll do another 10 minutes on the expression stuff, and we'll review that more next time. It's also in the project description as well, how that works. But I want to show, you know, the kind of conceptually how the expression stuff works. Okay, so here's our program. Don't worry so much what it does yet. And actually, let me take a simpler program, and you have both of these examples available to you. So this is a program. All it does is it's just the main method, and it just returns 1. Here is the assembly code that your Simple C compiler will produce. So just to review it, it emits the prologue, creates stack space for the argv and argc. Don't worry about that yet. And at the epilogue, it restores the stack pointer and restores the base pointer. In the project description, I've given you first how you actually use the compiler, which I think you should sort of know by now how to use this. But you run your compiler, save it as a .s file, that's an assembly file, compile it, and run it. So you run it like this, and this is how you view the return code of the program. But assuming you've already gotten your Simple C program compiled to assembly, and if you want to turn it into an executable, you use GCC with the assembly file, and it'll give you an a.out file. So okay, so just read the directions, review the directions for how to do that. Here's how we use our debugger. So the very first thing I think you should do, I recommend doing strongly, is download and set up this PEDA, what do they call it? Assistant for GDB. So you just clone it and follow the installation directions. Very, very simple. Just a couple lines for installation directions. So once you have PEDA compiled and you have your compiled version, well, let me do simple too. Once you have a compiled version of your assembly, start up GDB using GDB. Then we're going to set a breakpoint for the main method, so that will start running and then stop at the beginning of the main method. Use run to run the program. And so the nice thing about PEDA is it gives you, it's a little overwhelming to look at at first, but there's really just three sections here. There's the set of registers, all the registers that you in the machine. There's the assembly code, the point at which your program counter is in the code. So this little arrow here says, I am now at this instruction. I'm about to execute this instruction. I haven't executed it yet, I think, or I'm at this instruction, I'm about to execute it. And it shows you the assembly code before and after it. If you look at our assembly code, you can see we're now right here inside of our function. And then it shows you the contents of the stack. So it has everything you need to trace a program and also get some understanding of how this function call ABI works. So be aware that this stack is a little confusing because the top of the stack is here. So its lower addresses are at the top versus the diagrams we see for stack and heap. There'll be other grading scripts for this as well. Somebody asked about grading scripts. But okay, so you have your registers, code, and stack. Everything you need to know about what your program is doing during execution. So remember, this is the program that we compiled with simple C into an assembly program, and then we turned it into an executable using GCC. So this is not what the compiler does. This is running the code that the compiler produces. Okay, so let's step through it. Okay, so what's the value of RBP right now in our compiler or in our running program? So we've already pushed RBP and updated the stack pointer. So where do we find the value of RBP in this output, or what is it? Can somebody see what RBP is right now? And while you look at that, I'm actually going to, so somebody's saying 55129. So that's the value of our AX. But remember, the base pointer is called RBP. And I'm actually going to do, a different program so you can see the So sorry, give me 1 second. I want to enhance these instructions a little bit more. I realize that this is in Intel syntax, which is going to be royally confusing. The syntax is going to be different. So let me update the instructions to do that. Breakpoint at main, run it. Okay, so again, the same question, RBP, what is or I already told you the answer, but what is the value of the base pointer right now in the program? Any takers? The value of the RBP right now? So if you take a look at this, so recall that these are all your registers. So what's the register name of the base pointer for the base pointer? I think I'm losing people after a couple hours. So the base pointer is held in the RBP register. So we put it in RAX temporarily when doing, looking at a parent scope, but the RBP register is expected to always hold the base pointer. Yeah, so somebody's asking, is the red number RBP or not? Okay, yeah, so this is a good question. So this PEDA tool goes a step further in from showing you the value of registers. It also shows you the contents of what those registers point to. So if we just look here on the right after the name of the register, this is the actual value in hex of that register. So RBX right now holds 0. RBP holds 0x, 7 FFFFD160. This PEDA helper for GDB also shows you with this arrow, well, this is the value of the memory that it points to. So yeah, the blue numbers are addresses, red numbers are values. And so GDB is really good at figuring this out. So blue is, and actually I didn't realize it was color coded until you guys mentioned this, but yeah, blue is an address, red is a value, although this looks like an instruction pointer value. Okay, well, anyway, I'm not sure if that color coding is exactly right, but this is the value of the register. If GDB realizes it's a pointer, it will also show you the value of the register that it points to. Yeah, so exactly right. So RBP is this address ending in D160, and that address, D160, has its value in it. And it does, oh yeah, you're right. There it is. So red is code data. Yeah, good. I didn't even notice that. I haven't seen this before. But okay. So they're distinguishing data from value. So I guess if they realize that it's not an address, they'll put it in white. And yeah, I mean, they're all data. It's all data, but. Okay, so RBP right now has this address. Now, can anyone tell me what the top of the stack, the value is for the top of the stack? It doesn't actually show you the real address here, but what is the value stored at the top of the stack? This is a tricky one here. So retq, where's retq? I don't even see retq. Where do you see ret? Oh, here. Okay. So this is the top of the window on the code. So that's the code section. But what about the stack? So recall that the stack is here. So what is the value on top of the stack? Okay. So somebody, there are actually two ways to look at this. So the stack pointer always points to the top of the stack. And at this point it holds, notice it's the same value as the base pointer because we moved the stack pointer into the base pointer, so they hold the same value. And that points to something in the code segment. Or that looks like it's a code segment. But anyway, so another way to look at this is the stack here also shows you the top of the stack here. This shows you the top of the stack. So you can also see that the value here is wait, I'm confusing myself here. Sorry, this is the address in the stack. So that's the same as the stack pointer value. And this is the value in memory at that stack pointer. I think I got that right. Yeah, so this stack representation is, yeah. So this is the top of the stack, the lower address in memory. Yeah, for better, yeah, I know this is confusing because usually we show the stack growing down. This shows the stack growing up. Whew. Okay. All right, mostly with me so far. So let's step through this. Yeah, how a stack should. Yeah, exactly. So let's step through this. So I'll do step I. Okay. All right, so let's get to calling function f. So in here, don't worry about what all this code does, but at some point we're going to call function f. So let's look at how this works when we call function f. So I'm just going to skip past some stuff here. So let's skip past all this, and I'm going to skip to the point at which we call f. Okay. So the first thing we do is we assign the parameter, RDI is the first parameter. We assign it to 3. So don't worry yet how this happens. We need to look at how expressions are done to do this. But just realize that this pop RDI is assigning 3 into RDI. So this is how we pass the parameter to f. Then we call f. And as soon as I call f, control is going to transfer to the place in memory that f's code segment is stored. So you can see here that it shows you an address, but it also shows you an offset from the main label. So we're 28 bytes from the address of the main function. So as soon as I do this call, oh no, 3. Oh yeah, I mean 03x has everything to do with it, but I'm just skipping over the expression. So that is what's happening. But let me do expressions. Let me do expressions later. Okay, so as soon as I call this, we're going to transfer control to another place in the code segment. Call will push the return address and then branch to the address of f, which here you can see it's 555555129. And we're going to see that it's not going to be apparent, but the addresses here on the left are going to change. So as soon as I do that jump, now you can see we're at a different address. Our instruction pointer is at a different address. Okay. So notice that what this call did is it, we don't see an instruction here because it's implemented in the call instruction itself. But the first thing the call instruction does is it pushes the return address on the stack. So you can see here that the return address is the first instruction after the call. So here's our call on the right. And the very first instruction after the call is push RAX. And you can see here that GDB helpfully tells us what the actual code at that address is. But the value on top of the stack is the instruction pointer of the next instruction after the call. So that's how part of the stack frame by the caller is updated. According to the ABI, we push the return address before we branch to the callee. So here is the next instruction pointer we want to run after the call is finished. That's the return address. And we can actually confirm here that this is the instruction pointer. The contents of that code is the same as the next instruction after the call. With me so far? You guys getting this? I think I'm going to have to do expressions next time. Yeah, you should use GDB. So I gave you instructions for using GDB. So it is a bit rough. So I think, I'm going to have to push back the expression stuff next time. I may just push back some of the project stuff because I'm realizing this is a bit intense, even simplifying the project. So somebody's asking to subtract. I'll get to subtract. So let me just make sure everybody's clear on this function call. So we pass the parameter by storing the value in RDI, which is the first argument in the Intel ABI. Then we use the call instruction. The call instruction at Intel, because it's CISC, it does two things. It pushes the next instruction pointer on the stack. That's our return address. And then it branches to F. So just to kind of keep this in mind, this is the, this stack frame is reversed. So sorry that it's, this in this stack frame, the top of the stack is at the low address here, and the high address is at the top of the picture. But this is how the return address got saved. So right now, our stack pointer is here, and it's holding the address of the next instruction in main, the push. Is this a little easier? You guys with me on this so far? After 3 hours, you may just need to go back and rewatch, and hopefully this will make sense. I know this is after, yeah, you're after 3 hours. So I'll finish up this function stuff. We'll see. We'll save the expression stuff for next time. All right, but let me finish going through this. So now we are at the beginning of F. We're about to push the base pointer, because remember, we're saving the stack frame of the caller. We push the base pointer, which updates the stack. So now our stack has a new entry, and it refers to the base pointer. So unfortunately, this is interpreting it as code. It's not actually code, but it's telling you that because this is for exploit generation, and the stack for exploits, the stack will have code on it. But you can kind of ignore this code part and just see the value here. This value is the address of the caller's stack. I'm sorry, this address is the address of the caller's stack. And if you interpret it as code, it points to some data. But if we were to look down this stack here, this is 110, D110. If we go all the way down to D160, that's where that's where main's stack frame is stored. So we've pushed the old value of RBP here. This is the old value of RBP. We've pushed it onto the stack. The next thing we do is we update the stack pointer. So this is, so somebody asked, this is hex 10, which is 16. So we're making space for both the, for the one parameter. So this here is making space for the parameter that we passed. So don't worry about push RBX. This is just part of the Intel ABI. And then the next thing we do is we save the parameter into memory. So we're taking the parameter, which is RDX, and we're putting it into memory using the same offset scheme that we used before. So it's selecting 16. Yes, that's exactly right. Yeah, very good. Yeah, so the RBP entry takes up 16 bytes. So yeah, exactly right. The RBP entry takes up 16. Wait. Oh, no, I'm sorry. The RBP entry takes up 8 bytes, and the, oh yeah, this should be 8 bytes, actually. This should be 8 bytes. This might be a mistake. But this is basically just allocating two 64-bit words onto the stack. Whether it's necessary whether it's necessary or I just made a mistake. The other 8 bytes is my mistake. So I've made this more confusing. Sorry about that. So this only needs to be 8 bytes. So let's, we're allocating 2 entries on the stack, but don't worry about that. Once we've saved the base pointer, yeah, the stack pointer, yeah, exactly. The stack pointer points to the beginning of the last element here. And then, this moves the parameter into its place onto the stack. So sorry for that. So definitely I'm gonna just push back the project a little bit because I also made these mistakes, and we're still working over the function call ABI. So I'll push this back. We'll push back the expressions to next time. And I mean, we can't push back well, we can push back the lectures a little bit as well. We might push back like a half a lecture to do that, and then push back some of the due dates. Okay, so I think that's plenty for today. That's 3 hours. Thanks for bearing with me. You can, of course, watch this again to work through it. The main thing I want to get across, though, is this part where you're saving the old base pointer and updating the new stack pointer, and then we'll continue on with the parameters and expressions next time. Yeah, let's worry about the parameters next time, because I made a little mistake here in subtracting by 16 instead of subtracting by 8. Yeah, so have a good weekend, everybody. I'll move to office hours now. I know this is very tedious. We'll get through it. Spend some time going through the debugger and walking through some of this assembly. You could even just take GCC compile without optimization. You know, take any program, compile with -0, you know, without optimization. I mean, it doesn't really matter if you do with or without. And then just step through the debugger with this debugger that I showed you, and you'll get a much better understanding of how this assembly works. All right, guys, have a good weekend. All right, Halloween tomorrow. So have fun, and I'll go to office hours in just a minute. Bye, everybody.